Hello, I am Jonathan Bishop, and here's my lab report for Lab 7. So we're given a star data file which is all the points that the star is at throughout its trajectory. We're given the star mass, a time step, and a black hole position. And from this, we're supposed to use our code from our last lab to calculate the black hole's mass, which I found to be about 2.8 times 10 to the 31 kilograms. Here's my code. I have the star's mass right here, same as before. I have the delta T, same as before. Position of the black hole, I defined what the G constant is. And here's my star data that I inputted into the code. And then let's skip to the good stuff. Okay, so I have velocity initial and velocity final defined here. From this, I'm able to find P initial, which momentum, and P final by just multiplying the star's mass by the velocity. And from this, I can find delta V and delta P. And then dP dt is equal to, it's basically the change of momentum over change of time. And according to the momentum principle, that is what F net is equal. And then I find the direction here, momentum direction, by doing the final momentum over the magnitude of the final direction. And then I find, from that I can find the magnitude of dP dt parallel, because it's the change in the magnitude of the momentum over delta t. And I multiply that, because it's a scalar vector, scalar value, I multiply that by the direction p hat, and then I get the the parallel, which is the same as F net parallel. To find the perpendicular, I do dP dt minus dP dt parallel, because the parallel and the perpendicular components added together make dP dt. And as before, dP dt perpendicular is the same as F net perpendicular, because F net is equal to dP dt. To find the distance between the star and the black hole, I subtracted the black hole's position by the star's position. I normalized that to find the direction of r, of the distance, and I took the magnitude of that so I could find the mass of the black hole. And to find the mass of the black hole, I use the gravitational formula. I already know G, I already know the distance, magnitude of the distance, I already know the force, I found that in the code above, and I already know the direction, and I know the star's mass. So basically, I am just solving for the mass of the black hole, and which I found, and then I did the gravitational formula right here. Okay. So I created arrows to represent the dPd parallel, dPd perpendicular, and the dP dt. Keep in mind that parallel portion is the same as F net parallel, and same with the perpendicular and dPt. So I'm going to run my code. There's my star, there's a black hole, here's dP dt, here's the parallel, and here's the perpendicular. And it gives me the mass of my black hole, which is right there. So I have to answer, what does this mean? How do these F net quantities relate to the dPd quantities? Well, according to the momentum principle, they're equal to each other. Therefore, this is equal to that, this is equal to that, this is equal to that. Let's discuss how they're different. Okay. To find the F net in this case, it's just the gravitational forces. So that you find answer to that through this equation right here. To find dp dt, you find it through, you derive it through another process using change in velocities, like I showed you in the code. See, dp dt, well, f net is equal to change in velocity over change in time times the mass, or mass times acceleration. So what if the black hole, I had a new black hole in the same position but nothing else changed? Can I still find the mass of the black hole? And yes, I can find the difference, because I'll have a new mass right here, which will come out to it'll give me a different gravitational force. And when I have that new gravitational force, I'll be able to solve for the mass of this new black hole, like I did in the initial problem. Okay, thank you for watching my video.